Hello students, this is Dr. Bhavani Regmi. In today's lecture video, we are going to continue our chapter 6. We are going to learn about reaction rate and how different factors affect the reaction rate. Okay, so let's get started. First of all, when we say reaction rate, we are talking about the speed of reaction, right? As I mentioned, some reactions are fast reaction, some reactions are slow reaction. Okay, the reactions like mixing two clear solutions and creating, developing the precipitate out of them that you do in the lab, that kind of reaction is fast reaction. Within minute, within seconds, you see the products of the reaction, right? Some reactions are slow, and some reactions will need some kind of initiation even to do the reaction. Okay, for example, aging, right? We age, we grow. It is a slow process. Ripening of vegetables and fruits, that is a slow process, right? Some reaction which can give us the great deal of energy, for example, the propane gas burning in oxygen gives us huge amount of energy, but still that reaction needs some initiation. You have to bring the spark to initiate that reaction, right? Otherwise propane gas is there, oxygen is here in the atmosphere. It does not burn all by itself. You have to input some initiation in there, right? So why certain reactions are slow, certain reactions are fast, we can actually talk about them in the key concept, okay, about activation energy. And we know few criteria that are needed for a reaction to occur, right? We know that first of all, the gas molecules, right, or reactant molecules should, the reaction molecule must collide, right, in order to have that collision. Once the collision occur, then only the bonds between them in the reactant will break down and the new bonds to become a product will form, right? So the basic criteria is we need to have the collision. Rate depends on the speed of reaction, how fast or how slow it occurs, depend on the number of collision. If we have more number of bang bang, right, more collision between the atoms, then more products can form. The probability of forming the product will be high if there is more collision between the reactant molecule, right? That was one of the criteria. Also, we need to have enough energy, right? There should be activation energy enough in order to break the bonds, right? So activation energy should be there. There should be at least the activation energy to cross over the energy barrier and form the product. And we call such collision who have the threshold energy, we call them effective collision. So regular collision only is not enough, right? We have to have more of the regular collision, and those collision must be an effective one, right? Then only the product can form. Then only we can speed up the reaction. That means the rate is always the rate of change of something, right? When we talk about reaction rate, we are talking about the change in the concentration of product over time, or the change in the concentration of reactants over time. That is called the reaction rate. Now, we can actually manipulate, we can actually increase the rate of reaction by increasing the number of effective collision. Okay, so how do we do that? We have several ways of doing that. Either we can increase the temperature of the reaction system, right? Some of the reactions are like, if we increase the temperature, now the molecules will have more collision because they run faster, right? They will have higher energy associated with them because the temperature will excite them. The particles will run faster, and when they run faster, they will have more energy that is associated with the motion, more kinetic energy, and now they have effective collision, means they have enough energy and they can form the product. Similarly, some other reasons, factors that we can manipulate is we can work with the surface area of the reactants. Higher the surface area, okay, greater the surface area, greater will be the number of collision, okay, and then greater will be the speed of reaction, okay. A simple example is, actually the dissolution is not a chemical reaction, but we can understand the concept from there. If you have a cup of water and you drop a cube of sugar in it, right, and then stir it and let it dissolve, and side by side if you have another cup of water where you add some powdered sugar, right, and then you have water in it, then you will see, if you mix them together, right, both of them, you will see the powdered sugar will dissolve much faster, right? The dissolution reaction is much faster because of the higher surface area in the powder. More the surface area, it means there will be more ways of contact between the particles, right? There will be more contact. When there is more contact, then the bond breaking and bond making things will be a lot easier, right? So we can simply understand that with this example. So increasing the surface area will increase the number of collision and will increase the speed of reaction. Similarly, the physical state means if you have solid or you are comparing between liquid and gases, okay, the particles, the reaction between them, the gas particles will be diffusing more, they will be running faster, and they will occur faster reaction, right, compared to liquid, compared to solid. Okay, so physical state also matter in the number of effective collision. The other factors are concentration of reactants and the use of catalyst. Actually, we are going to look into each of these factors in detail. So let's look into that. Okay, first of all, how the concentration affect the reaction rate. Okay, whenever we increase the concentration of reactant, it will increase the number of collision. So increase in concentration will increase the number of collision, right? And that means when we have more number of collision, more number of effective collision could be there, and then we increase the speed of reaction, right? So all these explanation we are doing, we are talking over the collision all the time, right? Actually, it is known as a collision theory. Okay, the explanation that we are talking here is the basis of the collision theory. Higher the number of collision, more will be the probability of crossing the energy barrier, and then reactant molecules will convert into product. Let's see that with one example here. Okay, you are burning some steel wool, okay, in the air, okay, and then you are burning it with the propane gas. Okay, what is happening is you will see the iron wool will just glow with a red hot, right, and then slowly and slowly the iron is converting into iron oxide. Iron is burning in the oxygen and converting into iron oxide. If you are doing the same reaction, but this time you are not doing on the lab open air, you are collecting the oxygen gas, let's say the oxygen gas in a Erlenmeyer flask. You have a flask that has full of oxygen, okay, and then you bring the red wool in it and then burn it. In that case, you will see an explosive reaction. The red hot steel will now burn very vigorously, and it will form the product iron oxide very quickly. Okay, so the difference is higher the amount of oxygen you are using for iron to burn with, faster is the reaction. right? So that's how increasing the concentration increases the reaction rate by increasing the number of collision. Okay, so now let us look on how the temperature affects the reaction rate. Okay, so whenever we increase the temperature, okay, increase in the temperature will increase the kinetic energy of the molecule. And whenever we have higher kinetic energy of molecule, more molecules will cross the energy barrier, right? Cross energy barrier. And then now you have in the energy diagram, right? If you remember the energy diagram that we have learned earlier, now more and more reactant molecules can cross that energy barrier and form the product, right? And that's why the speed of reaction will be increased. So increase in the speed of reaction, which is meant by rate of reaction, is enhanced. So temperature will always increase, means we will have average kinetic energy increase. That's how the reaction rate will speed up. Okay, because temperature is directly proportional to the kinetic energy of molecules. Okay, if you increase temperature, the kinetic energy will also increase. That's the reason. That's why we store food in the refrigerator, right? So that we slow down the reaction that causes food to spoil. If you leave the food outside on the kitchen island, right? If it is a hot day, the food will spoil in couple of hours, right? But if we put them in the refrigerator, it will be good for a couple of days, right? So by cooling the temperature, we are slowing down the reaction. By increasing the temperature, the reaction will speed up. Okay, so these are the two factors we just learned. Let's look on the third one. The third one is the catalyst. Catalysts are the chemical compound, okay, that will speed up the rate of the reaction. They will not be consumed in our reaction, but they will help the reactants to convert into product. It means they will get regenerated after the reaction is over. Okay, so a catalyst is defined as a substance that speed of the rate of the reaction. How do they work? As I mentioned, the catalyst will be recovered unchanged in a reaction. Okay, they will, like, if they are used up, they will get regenerated. Okay, that's why we say unchanged. They do not appear in the product, means the catalyst is, there is no change in the catalyst. The net change will not be there. Okay, so the catalysts are the substances that help to speed up the rate of the reaction. Okay, let's see with an example here. This is the reaction of organic molecule that you will learn in 1152, right? The second series of that. So here we have one of the reaction where we are using the element, the metal palladium, as a catalyst. Okay, if we want to do this reaction of ethylene, okay, CH2 double bond CH2 molecule, and we want to add hydrogen in them, without catalyst, this reaction is quite slow. Okay, but if you add a catalyst in the reaction mixture, then this hydrogen, okay, the H2 molecule is hydrogen, the bonds will break. One of the hydrogen will go to the first carbon, the second hydrogen will be added to the second carbon, and then we will have the product ethane, that is carbon with 3 hydrogen and next carbon with other 3 hydrogen. Okay, so that makes them ethane molecule. Okay, some disturbance is here. Okay. Okay, so let me try to see this. My pen is moving. And in nature, in biology, you will see we do have enzymes, right? Enzymes are the biological catalyst. Okay, we call enzymes the biological catalyst because they will speed up the biochemical reaction in our body. Okay, how do enzymes work as a catalyst, and how do the catalysts speed up the reaction? We will see in the next slide. Okay, the catalyst will accelerate a reaction, speed up the reaction by lowering the activation energy and without affecting the change in the enthalpy. What does it mean? Let's look with one slide, the example. Right? This is the energy diagram we have learned earlier. Right? In energy diagram, we have reaction coordinate on the x-axis, energy on the right, and then we draw hill like a structure to show that the reactant will go to the top of the hill to become the transition state, and then transition state will convert into the product. Right? So here the hill, the energy diagram with the blue color coded, is the one where the reaction does not use any catalyst. Okay, let's say the same reaction, this time we are adding the catalyst into it and let the reaction run. Now this time the products will form very fast. Okay, by the diagram you can see the catalyst will bring an alternative pathway, okay, alternative pathway in the energy profile, right, in the energy diagram with the lower value of activation energy. Now the hill is much lower in height. It means now more and more reactants can cross over that energy barrier, right, and can form the products faster. So it is always the catalyst reaction. Okay, the reaction that has the catalyst in them, we call it catalyzed reaction, will have a lower value of activation energy, and then the reaction will be faster. Okay, if the hill is too tall, right, not all of the atoms of the reactants can cross that energy barrier. But if the hill is shorter in height, I have to make the product on the same line, right, shorter in height, then now more of the reactants can pass over that reaction barrier, and form the product. Right? And during this reaction, either using the catalyst or not using the catalyst, the value of rate of reaction or the value of enthalpy change will remain intact. Okay, it will not be different. Why? Because delta H is the enthalpy of product minus enthalpy of reactant, right? Either route, either you use the catalyst or you don't use it, you start from the same energy level of reactant and you end up with the same energy level of the product, right? Both of these curves, they start from the same point, they end up on the same point. It means the delta H, right? This is same for the both reaction, either catalyzed or not catalyzed. Okay, so by using the catalyst, you lower the EA and you make the reaction faster. How cool is that? All right, so now let's look on how the catalyst or the biological catalyst, the enzymes, work in our body. For that, I'm taking an example of milk here. We have a cup of milk. The milk has the polysaccharide, okay, called lactose. Okay, lactose is the component that is present in the milk. And in order to digest that lactose, in order to break down that big molecule, right, we need to have the enzyme called lactase in the body. Okay, and all the enzymes, they do have a special kind of site. We call them active site in them. Okay, the structure of the enzyme, the protein, will be such a way that maybe something like a pocket, so that these molecules come here and they get stuck, right? And now the reaction, the breaking down of bond will be much faster when they are trapped in the active sites of the enzyme. Okay, so since the process of reaction is the breaking of bond and making the new bonds, right? So right away, in the presence of the enzyme, the lactose will break down into the simpler glucose and galactose molecules. Okay, it means now the lactose is digested, right? So here the enzyme lactase act as a catalyst, right? It drops the height of the activation energy and we have faster production of products. Okay, so you might have heard of people who are lactose intolerant. They have to drink the milk that is lactose free. Actually, lactose free milk means they have added lactase enzyme in that milk, because those people do not have adequate amount of enzyme in the body, right? And due to that, they suffer from the intestinal issues, right? Discomfort when they drink milk. That's why they have to drink the lactose free milk, means the one that has lactose added to them. So now, since the lactose is present there, it will be digested, and that's how it will be taken care of. Okay, so we saw 3 or 4 different factors that is speed of the reaction, right? We looked into the temperature, concentration, we talk about the surface area, and finally we talk about the catalyst, how these different factors speed up the reaction. Right, you will learn about the inhibitors. Maybe in biology class, the inhibitors are like negative catalyst. They drop down the speed of reaction. Okay, but that is not covered in this syllabus, so we don't have to talk about it. So yeah, we talked about different factors that is speed of the reaction in today's lecture. Okay, thank you.